Hello everyone, how's everyone doing? Good. Hope everyone is having a good KubeCon so far. My name is Vijay Samuel and I'm a principal architect at eBay's Reliability Engineering Group.
I'm Sandeep and I'm one of the lead engineer of the observability platform at eBay.
And we are here today to talk about retrofitting OpenTelemetry collectors in Prometheus and talk about how we have gone about adjusting to the scale at which we operate at eBay and how we overcome some of the scale/design limitations that we saw in both of these projects. So we'll talk about 3 use cases, the first one being Service Graph Connector, the next one being Prometheus exemplars, and then Prometheus itself and how we went about doing clustering. Let's talk about Service Graph Connector first. So refresher, Service Graph Connector is one of the connectors available in the OpenTelemetry Collector contrib project. And it's typically used to construct, as the name suggests, a service graph, which provides all the edges and nodes between the various microservices, databases, message queues that are involved in a distributed trace. Where would this be useful? If you're looking to know what the exact call chain is and you're trying to do some automation in terms of, okay, I have an incident that's going on a particular service. I'm going to walk either upwards or downwards to see where the increase in calls is coming from or where the most amount of latency is being spent, were there any changes that were executed in any of these services in the call chain. For a lot of causal analysis, a service graph is very useful. And as we go into more automation with things like AI, a service graph is paramount for being able to successfully do causal analysis. So what the service graph essentially does is it processes all the spans, constructs the call graph, but with an important caveat. It needs the entire trace to complete for it to be able to generate a complete call graph. And when you're running at scale, say 10 million spans per second, and spans coming in from hundreds of Kubernetes clusters, like how things are set up inside of eBay, waiting for the trace to finish at that scale in memory is a tall ask. You need a lot of memory because there is a lot of latency patterns that are there. Some finish at 5 seconds, some finish 50, some finish 5 minutes. Do we wait for that long before we start processing? If yes, that's a large amount of memory that is required. So what we ended up doing is we have a trace store where you have OpenTelemetry collectors that are there. They write to an ingest gateway that we have written, and that gets written into shards. So shards, for all practical purposes, are a bunch of ClickHouse pods that form a ClickHouse cluster. And we also have a metric store. Sandeep will talk about how the metric store is laid out a little later. But you have OpenTelemetry collectors that write to a gateway, and from the gateway we aggregate and then write into a metric store, which is in this case a cluster of Prometheus pods. So what we did is we wrote a receiver, an OpenTelemetry receiver that reads from ClickHouse periodically using simple select star group by trace ID, and then you put in the service graph connector in that receiver. So when you do this, what is essentially going to happen is that you already have traces that are completed sitting on ClickHouse. You are streaming them into an OpenTelemetry collector, construct the service graph. At this point, you don't need to hold things in memory. As and when things are coming in, you can construct the call graph, and then you can just write the call graph into Prometheus, which OpenTelemetry collector supports. Yeah, so because we were we are doing this, we wait for the traces to finish in storage, and then we pull traces with a reasonable offset. So typically we do 5 minutes because we feel that 5 minutes is reasonable enough time for most of the calls to complete. For all the anomalies, we frankly don't care. We'll find a different way to solve it in the future. And the custom receiver just simply does select star every 5 minutes. So this basically allows us to not tamper with the service graph connector that's available in OpenTelemetry contrib. The periodic poll is very efficient on memory. And given the scale of which microservices are laid out inside of eBay, we have roughly about 4,000 microservices. And one of the expectations of most deployment architectures with the OpenTelemetry collector is that the request starts and finishes within the same Kubernetes cluster. But at scale, that is not practical to achieve, given there can be tens of databases, hundreds of microservices that are talking to each other. Our deployment pattern is always cross-cluster. Communication is very common. So with this pattern of pulling from storage, we don't need to worry about that. Some patterns also, what they say is that you can globally route spans to a handful of OpenTelemetry collectors as a second tier, and then you hold in memory and then process. So this approach negates the need for that as well. Globally routing can be hard. If a pod dies, then you lose data and things like that. And this pattern can be used for other processors as well. For example, the tail sampler. Tail sampler also has the same expectation. You have to wait for the trace to complete in memory, and then you apply sampling constraints. If you use the same methodology, you can just wait for, you can have a hot tier of spans that are being stored for, say, 2 hours, 2 days, stream all of them into a secondary set of collectors, do tail sampling, and then store them in a different tier that has maybe 14 days, 30 days, or several months. So that's the first one. The second one is Prometheus exemplars. How many of you have used exemplars? And how many of you feel that it's valuable in your triage process today? Okay, few hands. Okay, good. So we use exemplars very heavily inside the company because exemplars as a concept is very powerful. A quick refresher on exemplars: they're a point-in-time representation or an event that has happened within the time series. So if you take request latencies as an example, Prometheus histogram represents the latency distribution across all the requests that are flowing in. But an exemplar is the representation of one HTTP request that occurred and its latency. So it would have a timestamp, a set of labels, the exact latency that request took, and basically that gets stored in Prometheus. And on the UI, if you're using Grafana or something else that you built, it would be represented as a clickable marker. So you click on it, and then it should be able to take you to the a representation of the actual request. And in most cases, an exemplar has a trace ID. So you click the clickable marker, and then it takes you to the end-to-end distributed trace. So a lot of the usage allows for drill-down based triage. So you have an alert. You look at the alert, you look at the series that was behind the alert, and if you said that, okay, if latency goes beyond 10 seconds, alert me, you would go and look for clickable markers that are greater than 10 seconds, click that, and then you analyze to see what essentially is going on. So in Prometheus, today, exemplars are stored in a circular ring buffer, and it's controlled by a flag called storage.exemplars. Being a circular ring buffer, it's really fast because it's in memory, but it comes with a key caveat that given that it's a circular ring buffer, you fix the total number of exemplars that can be retained. So you say 10 million exemplars, and that's about it. And the 10 million and 1th exemplar will basically rewrite the head, and it keeps going in a circle. And for us, this typically gives us maybe a few hours, or even in certain cases like 15 to 20 minutes worth of exemplars. So if you're viewing a graph that's say 2 days long, the first 15 minutes has a bunch of exemplars that are there, and then after that it is basically blank, because there is no persistence that's implemented into Prometheus exemplars at this point in time. There are issues that are open on upstream Prometheus. Some point, either through contributions of our own or someone else in the community, it should be reality, but our hope is to see how we can achieve the full potential of exemplars without having to modify Prometheus itself. So we want to be able to retain exemplars for weeks. So within the company, we offer 2 weeks worth of retention for traces, and we want to be able to provide at least 2 weeks of retention for exemplars, so that we can do the metric to trace navigation and then build triage experiences on top of that. So what do we do here? We took a non-intrusive approach for this as well, where we said that we are going to stream exemplars into ClickHouse, and we'll basically expose the same query exemplars API in the Prometheus compatible format. And for UIs alone, when they are requesting query exemplars, we'll basically, based on the user agent, we'll layer 7 route the queries into that standalone API instead of using the standard Prometheus exemplars API. So that way, if some automation wants real-time data, it will still be fed through the circular ring buffer. But for anything that's UI, which can take a couple of seconds longer if need be, it would come from this API that is querying ClickHouse. I think like there have been a lot of talks in the past about what would it take for time series to be stored in ClickHouse. There are a lot of pros and cons. Performance characteristics might vary, but one of the things that we have always seen in our installation is that performance characteristics of Prometheus are phenomenal, and it's very hard to beat because it's very, very purpose-built for time series being queried at scale. And as a result, when we first tried putting this whole thing behind ClickHouse, the queries were several seconds slower than what query exemplars API was in Prometheus. And so through various iterations and applying various techniques that ClickHouse or features that ClickHouse provides, we came up with the query that's there on the right side. And the gist of it is that we use dictionaries to store metric names. So the first thing we look for is if the metric name exists. If it doesn't exist, or if the metric name has an exemplar, only if it has an exemplar, it's going to show up in that particular table. So we do a dict_get to see if the metric name exists. If it does not exist, we can quickly short circuit. And that was one of the areas where there were a lot of slow running queries when we were trying to do table scans to figure out if a certain metric name had exemplars. And in most cases, it doesn't. Like, there are very few histograms that actually have exemplars unless someone has gone about instrumenting exemplars for pretty much everything. The second one we did is sampling. There can be hundreds or thousands of exemplars, but does it actually make sense for all of them to be streamed back, especially for a UI use case? How many of those exemplars can you actually perceive, or can the dashboard render without choking? So that became a realization, and what we ended up doing is we ended up sampling, and the way that we sample is that for every time window and every series hash, we basically try to get a uniform sample, which is what in the query there would be a city hash 64 of timestamp comma hash ID, and then we take 10% of that, the third but last line. And we also limit to say 1,000 exemplars, which for the entire time duration might be generous enough to get a good distribution of all exemplars that might have exist. And going against conventional ClickHouse wisdom to have a single table with every row and column, we went with a denormalized schema because we observed that had higher performance characteristics than a single table, where there is a series hash ID lookup, which has the series hash ID with all the key value pairs, the label key value pairs that are there. We take that and we only do hash ID based lookups on the table that has the actual exemplars themselves. So the benefits, as I mentioned, like we were able to do this completely non-intrusive, no customizations on Prometheus. Prometheus continues to behave the way that it does, but we get the benefit of being able to look at exemplars for the entirety of the lifetime of the traces themselves. And we also have another use case that we have talked about in past KubeCons, where we use the exemplars themselves to do tail sampling, where if the metric system decided that an occurrence of the HTTP request was useful enough to construct an exemplar, then we should store the trace for the lifetime of the exemplar itself. So every dots on the dashboard, if you click, it would still be there because we honored its existence and we are tail sampling it for a longer period of time. And this gives us a very good representative sample for all the kinds of requests, both based on latency profile and based on the unique kind of errors that were seen for the given application. So that said, I'll hand it over to Sandeep to talk about Prometheus.
Thank you, Vijay. Yeah, in the next few slides, I'll walk you through on how we can scale Prometheus if the data size grows. Let's take a look at the let's take a look at the simplest form. It's a single TSTV node. The metrics comes in, you just write it to the single shard what you have, it goes to the disk eventually, and you can query the data out of it locally. It works fine, there are no issues until you have to scale, until you have to add more and more data. Then you'll hit it with the limits. It could be the disk I/O, it could be the query bottlenecks. I'm pretty sure all of us have seen that there is only a certain limit on how much we can vertically keep scaling it up, right? And how do we solve this problem, right? The easiest thing we could think of is basically to shard it. Why have a single monolithic TSTV? Why not shard it? So instead of having a single TSTV here, we add more TSTVs basically. And instead of writing it to the one single shard, we now have an ingester endpoint. So all the time series comes into this ingester. The ingester basically discovers all the shards dynamically through the Kubernetes API server. And for the incoming time series, it does a XX hash on all the time series, on all the labels, and it finds the suitable shard to write the data to. Great, so with this, we basically, we have solved the scale problem. We can keep horizontally adding more and more shards and scale it up easily, right? So, but the next problem we land upon is, what happens if a shard goes down, right? We lose the data basically. If a shard is down, we lose the data. And even if it's intermediately, if the shard is down, we won't be able to query the data which was in that shard. How do we solve the problem? This is where the replication comes in. We basically add 2 more copies. The ingester now, instead of writing it to a single shard or a single region, it replicates it. It writes the same data to 3 different regions, right? So even if a single shard is down, or even if the entire region is down, we're still good. There are other 2 copies. The query layer basically can query the data from all the 3 regions, 2 or 3 regions it can decide to pick, and it can merge the data, and it can send the results back to the end users. Okay, this is good. So we have the higher availability now. So what next? The multi-tenancy. Right, so in the organizations nowadays, we have multiple applications, and each of the application could be of different criticality, and some of them you may want to isolate it, just because they're critical data, and you don't want to keep it in one of the default TSDBs where the other 100 applications go. All right, so what we could potentially do is add more and more clusters, right? Instead of having a single TSDB cluster, we add more and more clusters and pin certain applications or certain tenants to go to a particular cluster, right? This helps in two ways. One, definitely the isolation. You can put the critical ones in an isolated cluster, and it could have its own retention capability as well, right? That is one of the advantages. The second is, again, it helps to scale us more and more, right? You can keep adding more and more clusters here. Great. So what next, right? One of the problems with all of these things, what we have seen is, the data we are bringing in centrally. So, it can be originated, the data can be originating anywhere. It can be, let's say, originating in, let's say, LBS or potentially even EU or anywhere, right? So we bring everything to a central region. That means there's a cross-colo data transmission happening. And it also means the data is flowing through the load balancers. Right, so if the data flows through load balancer, then there is it's a potential point of failure. It adds the latency as well, and it increases the cost as well. How do we solve this problem? To solve the problem, we keep the data closer to the source. Where the data is originated, we keep the data there. Right, so within the region, we generally have more than one availability zone, so we can replicate the data between the availability zone for the fault tolerance part. Right, so now the data is basically kept in the same region. And there are definitely multiple regions. So right, and within the region, there is the availability zone for the fault tolerance part. Cool. So this definitely, as I mentioned, this solves the problem, the three problems which I mentioned about basically the latency, the bandwidth cost, and also the single point of failure. And now, you could ask the question: how do we query the data from? How do we know where the data exists? Well, the easiest option is to, just fan out to all the shards and all the clusters. But that's expensive. That's not going to scale at all. That's really not going to scale, right? So given we have so many shards now, so many clusters now, how do we solve this problem? The way we are going about solving the problem is basically our query layer is smart enough to know where exactly the data resides. It knows which cluster has the data and which shard has the data, right? With this, we basically can eliminate the fanning out part. And obviously, you'll ask the question: how does your query layer know about this? Right? This is where our the index filters, the index stores comes into picture. So the index store is basically inspired by the field hint index from the Google Monarch paper. And the way it works is, for every single time series coming into our TSTB, we generate the n-grams and the fingerprints out of the key value labels basically, and all these data is sent to the index store. Right, the index store, the query layer, before it talks to the shards or the actual TSTBs, it talks to the index store. For the given query, it generates the fingerprints, and it talks to the index store to ask which shards or which cluster has the data. So the index store gives all the IPs of all the TSTBs which actually has the data, and the query layer just talks to only those TSTBs, gets the data out of them, merges the data, computes the results, and sends the results back to the end users. And yeah, this is how we are able to scale the TSTBs and still make it fast, precise, and scalable. Let's look at some of the benefits, what we are getting out of all of these things. Now, the TSTB no longer is cardinality bound. We don't have to really worry too much about the cardinality. Instead of the TSTB scaling it vertically, we can do the scaling horizontally, can keep adding as many shards and clusters as needed. And definitely there is a more efficient scatter gather. We don't have to fan out the queries everywhere across all the shards. Right? Thanks to our index store, we know exactly where the data resides, and we call only those shards which has the data. And also, we pretty much have a near perfect horizontal scaling with the tenancy model, which I mentioned, and also the kind of clustering what we have. We can keep growing as much as it's needed. Right? And also it has inbuilt resiliency because of the replications, and we don't have to keep redesigning the system as and when the more and more data gets inserted. With that, I stop here and open for any questions.
Yeah, feel free to use the mic in the center if you have any questions.
Is the index store also across the region?
I can repeat the question. The question is the index store stored in all the regions? Yes, we have region local index stores that are there, and then they basically bubble up all the fingerprints to a global index store. And the global index store is what is being used by the queryers to make the actual queries.
Hi there. Thanks for the talk. As someone who's not familiar with exemplars, I'm curious how sampling is done to avoid a lot of data that I don't care about. Most of the time, I'm less interested in 200s that complete within expected response times, and I care about abnormalities. Is that something that's done? It didn't sound like it was something that was handled in your specific sampling logic, but I heard something about how maybe there is logic to determine what is selected as an exemplar to begin with.
Yeah, so exemplars are selected by the Prometheus or the OpenTelemetry client itself. So whenever you say observe a certain histogram with exemplars, it basically randomly picks from the request and then it sends it out. On the query side, we only abide to the Prometheus contract itself. Query exemplars only takes a label selector. So if you say application equal to foo, status code equal to 404, then it's just going to pass that to us, and then we do a label selection. That's it. So given that Prometheus does not allow you to filter based on any binary operation or whatnot, that is not a capability that we have as well.
Thank you.
What's the ingester that you're using?
The ingester is nothing but a simple Go program that abides to OTLP. So there are some organization level policies that we need to put in place, like rate limiting and then deny list, allow list, and things like that. So it just exposes an HTTP service with OTLP format and then does all these additional policies and then writes them to storage.
So you wrote it yourself?
Yeah.
Okay.
Hey, my question is, how do you choose the TTL for the indexer for the data? So how do you know when the data is gone and you don't need it in the indexer?
So some of it is done through series lifecycle callback. We implement that inside our implementation. So the Prometheus TSDBs themselves is very similar to how things like Cortex work, where they take the Prometheus library and then expose APIs on top of it. So we have the ability to add series lifecycle callback to know when to add a fingerprint. Removing fingerprints is just with the retention policies. So once the retention policy expires, then the fingerprints get removed in bulk.
Thank you.
Hi, my question is about span metrics connector. So you mentioned benefits about service graph connector, but did you test anything about span metrics connector?
Oh yeah, so we use span metrics connector as well because if you turn it on, then you get red metrics for every application that's emitting traces, regardless of if they are emitting metrics or not. As in like purpose instrumented metrics. So it's pretty useful, and we have it running on all our OpenTelemetry collectors as well. And they in turn expose exemplars as well. So for every kind of unique span with unique status code and whatnot, we get exemplars for them as well.
Okay, so your span metrics connector exposes your exemplars.
They also emit exemplars. So raw instrumentation that every application has some exemplars that are being emitted along with the span metrics connector as well.
Okay, thank you.
Sure.
Thanks for the presentation.
Thank you.
Could you please comment on how your query layer compares to queries found in highly available Prometheus solutions in the open source like Mimir or Thanos?
We haven't done a benchmark that compares the two of them, but that is an exercise worth doing. Like the field hint index is not something that some of the high available implementations expose outside. If I'm not wrong, I'll need to verify. But like if they do not, that is a key difference maker, because like standard HA implementations, they do like scatter gather across all shards, and when you have 100, 200, 300 shards that you have to go through, it can become very expensive. So that is something that I feel we do differently.
Thank you.
In the beginning, you talked about feeding the traces to a trace store. What trace store are you using?
We use ClickHouse. ClickHouse.
Ah, thanks.
Yeah, but we don't use the standard schema that is advertised on the OpenTelemetry collector. We use a slightly different schema, but for all practical purposes, ClickHouse. This methodology can work even for a use case that uses the standard ClickHouse exporter. And if there were a ClickHouse receiver that can pull in the same format, then you can establish the same chain that we are establishing.
And you're feeding directly from the collectors into that, your custom collector?
So we have a custom exporter that writes into our ingester, and then ingester writes into ClickHouse. Because similar to what we talked about clustering with Prometheus, we have our own way in which we cluster ClickHouse clusters as well, where we don't have one large cluster, but small clusters which we can manage at scale. So we have a custom ingester that can recognize that. But yeah, that's how we do it. Like for the customer, it's standard OpenTelemetry collector that sits in the front, and standard Jaeger APIs that sit on the query end. And in between, we have some secret sauce that can scale things out.